Okay, physics. So we're going to get into vectors and describe. We're going to have two different ways of dealing with and looking at and representing vectors in this class. And let me expose you to what that's going to look like. So we have a traditional way of looking at vectors. Remember, a vector is something that's going to have magnitude and direction. So for instance, in this diagram here, I have vector A, and formerly we'll put an arrow across the top of the variable to indicate that it's a vector quantity. So anytime you draw velocity, it would be appropriate to put an arrow across the top. I just can't be bothered to do it, so imagine it's there. Same thing for B. So I can have two vectors, and I can add these together. So we'll do simple manipulation. So I can either take these and dissect them into components. So I can decide, well, how much is in the X and how much is in the Y. So we'll do this for projectiles. Anytime you have a velocity, for instance, is going off at an angle, you're going to have to separate it into a horizontal and vertical velocity. I can add vectors together or subtract them, right? So if I add two vectors together, I'll arrange them head to tail, and I'll get the resultant vector, which is the sum of those two. If I'm subtracting, I'm just going to invert one of those, so I'll make one a negative. So if I was to subtract B from A, I would end up inverting A, making it negative, so it points in the opposite direction, exact opposite direction, 180 degrees. So this is a common way of representing vectors, and if you've taken physical science or physics before, you've come across this description of vectors, and the only thing we're adding in here is this little arrow on top. Otherwise, it's the same idea. However, we have a more sophisticated way of representing vectors. So notice here that I can break A and B into X and Y components. And someone decided years ago that wouldn't it be better to just describe the vector in terms of components. So this is called a unit vector. So it's a way of describing a vector. And we're not going to use X and Y because it's already used. So we're going to come up with new terms. But the idea is that the same idea that we can describe a direction in two dimensions by describing on a coordinate system, and instead of X we'll use I, instead of Y we'll use J. And the nice thing about it is that you can go into as many directions and as many dimensions as you need to. So we'll do I, J, K, but you could the math is going to be the same for adding in 3, 4, 5, 6, 7, however many different dimensions you feel like working in. Yeah. Okay, so a unit vector. So we're going to describe the same sort of idea, but we're going to describe components of a vector, which makes it a little bit easier to deal with. So say I have a vector that's going off at this sort of angle. I can describe it as saying, well, it's kind of going in this direction. I'll call that the I direction. I'll put a hat on there. And this is going in this direction. I'll call this a J direction. I'll put a hat on there. So if I have a vector that is moving, I don't know, one I, one J, the length of this would be root 2. So hopefully you recognize that from using the Pythagorean Theorem. So this is the idea that instead of having a vector, say this has 10 meters per second going to the northwest, I'm going to describe a vector which is going to be, well, it has what's root 10? Oh, I know, so 3 meters per second in the I direction plus 3 meters per second in the J direction. And this is a different way of describing it. So the unit vector is describing individually. We could, this is in 2 dimensions. I could describe it in 3 dimensions. I'll use K, and that's really all we're going to ever get into. So there are going to be, I guess, just a handful of things that we're going to do with unit vectors. So one is you need to find the length. So notice in this traditional way of describing a vector that I'm telling you the length, and you can figure out the components if you have it at an angle on a particular XY axis. But in this way, we may want to find the magnitude of that vector overall. And to do this, I'm going to use Pythagorean Theorem, right? So hopefully you remember that for a right triangle, c squared equals b squared plus a squared also works for other things as well. So if I have 3 vectors, or a vector that's described by 2 components, I can find that my length is going to be square root of my I component plus my J component. But I can just add another one in here, right? So the math is easy. So if I wanted to find the length of one that had 3 dimensions, well, I'm just going to make it a little bit longer. I'm taking the length of my I segment plus, squared, length of my I segment squared plus the length of my J segment squared plus the length of my K segment squared. And if I take the square root of all of that, then I'll get to the magnitude of length. So notice we're dealing with a coordinate system. I think of I as x, j as y, and k as z. So I'm thinking about a coordinate system that's all right angles to each other. So the Pythagorean theorem still functions for that. So one thing we'll do is provide length. Second thing we'll do is that we'll need to add and subtract. So this is really simple. So this is one of the advantages of these unit vectors. If I have 3i plus 4j, and I want to add that to 2i minus 3j, right? Well, I just add the i's and I add the j's, right? So I can, this is going to end up being 5i, right? I add these together, and 1j, right? So just as we were combining vectors graphically before, so we can do this mathematically, and it's dead simple, right? So I can take these two. If I was to subtract them, then I would essentially multiply everything by -1, and then just add them together. So essentially you're taking 180 degrees of that vector and adding them together, the same as we would do for a traditional vector. There are a couple of things that we're going to do, but not quite yet. So we're going to multiply vectors. Okay, that's where the fun begins. And we're going to have two different ways of doing that. So one way is the dot product, which is the simpler one, and we'll use that this semester a few times. We'll come across the dot product where we're going to have, I don't know, a vector L, and we'll dot it with R. And the dot product is going to give me a magnitude. It's going to give me a number, but no direction. And we'll use that when we get into energy. We'll use the dot product, and we'll describe how to do that. We're also going to get to the point where we want to multiply using the cross product, and this is more second semester. But and again, the cross product is another way. So I'm going to write this L cross R, and that's going to give me another vector out of that, which is going to be orthogonal to the two vectors. So dot product, we'll get into a little bit. This one is just going to give me a number. We'll use an energy. Energy is just a number. It doesn't have a direction. But cross product we'll start getting into primarily second semester. So hang on. We're going to do more complex things, and I'll probably remind you about how to take those when we get to doing them. For now, we just have to deal with unit vectors, and there's really only two things we're going to be doing. So I need to find the length of my unit vector. So using the Pythagorean Theorem is the many dimensions as you need, and then adding and subtracting them, which is dead easy. So you should be able to do that. Anyway, don't get scared. So the I, j, k, they don't mean anything. It just means in that dimension, and otherwise it's going to behave just like a vector. And I hope that makes sense. We'll talk to you soon. Bye.